Vibrations produced in a string. We know that student, previous lecture we have seen about open pipe and closed pipe. Now we have to see about string. So consider a string of length L stretched between two rigid supports. The linear density, that is mass per unit length of the string, is m, and the tension capital T acts on string due to stretching. If it is made to vibrate by plucking or by using a vibrator like tuning fork, a transverse wave can be produced along string. So when wave reaches to fixed ends of the string, it gets reflected with change of phase by pi radians. So the reflected wave interfere with the incident wave and stationary waves are formed along the string. The string vibrates with different modes of vibration. If a string between two rigid supports and is plugged at its center, the string vibrates as shown in figure 6.11. See this figure. It consists of an antinode formed at center and node at two ends with one loop formed along its length. If lambda is the wavelength, then L is the length of string we get. So length of loop is equal to lambda by 2, because one complete loop, that is lambda, so its half will be lambda by 2, which is equal to L. So lambda is equal to 2L. The frequency of vibrations of string, that is N, is equal to V upon lambda. So we know that lambda is equal to 1 upon 2L and V is under root T upon M. V is the velocity. This is the lowest frequency with which string can vibrate. It is the fundamental frequency of vibrations or first harmonic. So N is equal to 1 upon 2L into under root Tm, capital T upon M, that is the fundamental frequency of first harmonic. Now if center of string is prevented from vibrating by touching with its lighter object and string is plugged at point midway between the one of the segments, if string vibrates as shown in figure 6.11b, see this second figure, then two loops are formed in this mode of vibrations. There is a node at the center of the string and its both ends. So if lambda 1 is the wavelength of vibration, the length of loop is what? Lambda 1 by 2 is equal to L by 2. So lambda 1 is equal to L, that is two loops are formed. So that frequency of vibration is given as N1 is equal to 1 upon lambda 1 into under root T upon M. So N1 is equal to 1 upon L into under root T upon M. Now if you multiply to this equation 2 and divide by 2, okay, you will get 2 into N. So you will get this type of value, okay. Comparing with the fundamental frequencies, okay, we get N1 equal to 2N. Thus the frequency of first overtone or second harmonic is equal to the twice the fundamental frequency, that is N1 is equal to 2 times of N. Now the string is made to vibrate in such a way that three loops are formed along the string as shown in figure 6.11c. So you can see this figure 6.11c, okay, where three loops are formed. If lambda 2 is the wavelength, okay, if lambda 2 is the wavelength here, length of one loop is what? Lambda by 2 is equal to L by 3. So lambda 2 is equal to 2L upon 3. So the frequency of vibration is what? N2 is equal to 1 upon lambda 2 under root T upon M. So N2 will be is equal to 3 upon 2L under root T upon M. So comparing with the fundamental frequency, we get N1 is equal to N2 is equal to 3N. So that is N2 nothing but second overtone, or 3N is equal to third harmonic, which is thrice the fundamental frequency. So similarly, For higher modes of vibration of string, the frequencies of vibrations are what? 4n, 5n, 6n, etc. Thus, all harmonics are present in case of straight string, and frequencies given by nothing but np is equal to p into n, where p will be what? P will be 1, 2, 3 up to infinite values you can take. So by using n is equal to 1 upon 2l, okay, whatever formula we have seen this here, 1 upon 2l under root t upon m, okay. So that is nothing but your laws of vibrating string. So on the basis of that, there are laws of vibrating string. See that the fundamental frequency of vibrating string under tension is given by n is equal to 1 upon 2l under root t upon m. So first law of length, that is fundamental frequency of vibration of string is inversely proportional to the length of the string. If tension and mass per unit length are constant, then n is inversely proportional to the length, where t and m are constant, or nl is equal to constant, that also you can write. Then law of tension, the fundamental frequency of vibration of string is directly proportional to the square root of tension. If vibrating length and mass per unit length are constant, then n is directly proportional to under root of t if m and l are constant. So n upon under root t is equal to also constant. And then next one, law of linear density. The fundamental frequency of vibration of a string is inversely proportional to the square root of mass per unit length, that is small m, linear density. If the tension and vibrating length of string are constant, then n is inversely proportional to under root m. So that is n into under root m is equal to constant. So if r is the radius, rho is the density of material of string, then linear density is given as, linear density is nothing but about mass per unit length. So volume per unit length into density. So pi r square L upon L into density. So L will cancel out. So n is inversely proportional to under root of m if t and m are constant. So we get n is inversely proportional to pi r square into rho in square root. So n is inversely proportional to the square root of density, and n is proportional to the 1 upon r, that is the radius of the wire. So the fundamental frequency of vibration string is inversely proportional to the radius of the string. Second, square root of the density of material of vibrating string. So these are nothing but your laws of vibrating string. So on the basis of string, okay, which we can see the explanation of this experiment, that is sonometer, which we are going to study in our laboratory. So in practical you have this experiment. So if you want to see this experiment, you can see its video on YouTube also. You will get very nice videos with explanation. So sonometer. A sonometer consists of a hollow rectangular wooden box called the sound box. See, this is nothing but your sonometer box. Okay, experimental setup of sonometer box. The sound box is used to make a larger mass of air vibrate so that sound produced by the vibrating string, so metal wire in this case, gets amplified. The same principle is applied in the string instruments such as violin, guitar, tanpura, etc. There are two bridges P and Q along width of box which can be moved parallel to the length of box. A metal wire is uniform cross section runs along the length of box over the bridge. It is fixed at one end and its other end passes over the pulley. So if you see that yellow color weight, so that is your pulley. Okay, so at the top its heading is there, pulley. A hanger with suitable slotted weights can be attached to the free end of wire. By changing the weight, the tension in the wire can be varied. The movable bridges allows us to change the vibrating length AB of the wire. So by using these bridges you can move its distance, okay, either you can increase it or either you can decrease it depending upon the reading. Now if the wire is plugged at point midway between the bridges, transverse waves are produced in the wire. Stationary waves are produced between two bridges due to reflection of transverse wave at the bridges and their superposition. Thus, portion AB of the wire between two bridges P and Q is the vibrating length. So, wire can also be made up of vibrate by holding a vibrating tuning fork near it. So, frequency of vibration is then same as that of the tuning fork. If this frequency happens to be one of the natural frequency of the wire, standing waves with large amplitude are set up in the wire since two vibrate in resonance. So this is nothing but your resonance. Now to identify the resonance, a small piece of paper known as rider, capital R, is placed over the wire at a point in the middle of the length AB as determined by the position of the bridges P and Q. If frequency of tuning fork and the fundamental mode of vibration of the wire match, this is achieved by adjusting the length AB of wire using the bridge P and Q. Now the paper rider happens to be at the antinodes and flips of the wire. So sonometer can be used to verify the laws of vibrating string. So first of all we will see about first law of vibrating string. So by measuring the wire, length of wire and its mass per unit length m is determined, then wire is stretched on the sonometer. And the hanger is suspended from its free end. A suitable tension capital T is applied to the wire by placing slotted weights on the hanger. So the length of wire L1 vibrating with the same frequency N1 as that of the tuning fork is determined as follows. So light paper rider is placed on wire midway between the bridges. Tuning fork is set into vibration by striking on the rubber pad. The stem of tuning fork is held in contact with the sonometer box. By changing the distance between the bridges without disturbing the paper rider, frequency of vibrations of wire is changed. When frequency of vibration of wire becomes exactly equal to frequency of tuning fork, then the wire vibrates with maximum amplitude and paper rider is thrown off, and that is nothing but your resonance. So in this way, a set of tuning forks having different frequencies, that is N1, N2, N3 dash are used. Corresponding vibrating length wire are noted as L1, L2 and L3 by keeping the tension constant T. So we will observe that N1 L1 is equal to N2 L2 is equal to N3 L3, which is equal to constant. So for constant value of tension capital T, mass per unit length is m. So NL is equal to constant if T and m are constant. So first law of vibrating string is verified by using sonometer. Now second law of vibrating string. The vibrating length L of a given wire, mass per unit length m is kept constant for verification of second law. By changing the tension, the same length is made to vibrate in unison with the different tuning forks of various frequencies, that is, if tensions T1, T2, T3 up to infinity, so corresponding to frequencies N1, N2, N3, etc., we will observe that N1 upon under root T1 is equal to N2 upon under root T2, which is equal to N3 upon under root T3 is equal to constant, that is, N upon under root T is equal to constant. So N into L, or you can write N is proportional to the square root of tension if L and M are constant. So this is the second law of vibrating string. So in this way you have to vary tension, and in first law you have to vary length. Now third law, that is about we have to vary different term, that is mass per unit length also you can vary. So verification of third law by using vibrating string, okay, that also you can see now. For verification of third law of vibrating string, two wires having different masses of length M1 and M2. So we can take two different densities of wire, that is linear density M1 and M2 are used. The first wire is subjected to suitable tension and made to vibrate in unison with given tuning force. The vibrating length is noted as L1. So using the same force, the second wire is made to vibrate under same tension and vibrating length L2 is determined. Thus, frequency of vibrations of two wires is kept same under the same applied tension T. It is found that L1 into under root M1 is equal to L2 into under root M2. That is, L into under root M is equal to constant. So by first law of vibrating string, N is inversely proportional to 1 upon L. So we get that N is inversely proportional to the under root of M. Then if T and L are constant, this is the third law of vibrating string. So in this way, laws of vibrating strings are verified by using sonometer experiment. So all these experiments we are going to perform in our laboratory. So before that, if you want to check it, okay, so you can check its all videos or its experimental setup or its basic information on YouTube also. Fine. Thank you, student.